All right, so last time we started talking about Boolean expressions. Boolean expressions are necessary for us to solve our second way human beings solve problems, that is asking questions. So in Java we call this conditionals. In Game Salad we call it rules. So a Boolean expression is any expression that boils down to a single value of true or false. Now in Java we looked at the generic syntax for asking a question. So let's pop over to Eclipse real quick. By real quick, I meant not very quick at all. There, we'll let that guy cook for a few minutes. So if we're going to show an example in here then, create a text field. In a language like Java, we might go ahead and define a couple of variables. Int a is equal to 5, int b is equal to 7, something like that. And then we might ask a question. We might say, if a is less than b, good enough in the absence of Eclipse. All right, so this is some Java code that defines two variables, or in Game Salad speak, two attributes, one named A, one named B. It's set A equal to the value 5, set B equal to the value 7. Then we ask a question. In Java, this is a conditional if statement. In Game Salad, it's called a rule, which we haven't seen yet, but we'll look at them today. So we're asking the question. Questions require a Boolean expression. Boolean expression is any expression that boils down to a single value of true or false. So in this case, we're asking the question if a, which is a variable, which boils down to the value, in this case 5, is less than b, which is a variable, which boils down to the current value of 7. So if 5 is less than 7, which is a true statement, we're going to go ahead and display to the screen a is less than b. Otherwise, we're going to display to the screen a is greater than b. And this otherwise is optional. We don't need to put in an else if we don't want to. And let's just see if this guy was done cooking by now. All right, so we'll just do this real quick. Well, here, we'll leave it at this for right now. So I defined my two variables. I asked the question, only if this Boolean expression boils down to true will I execute the body of this conditional. So in this case, 5 is less than 7, so this program should output A is less than B to the screen. A less than B. All right. Man, it's Eclipse is really struggling today. We'll just let it keep cooking, I guess. All right. Had I changed that A to be 50, and I left the code the way I had it before in Eclipse, where I just had the if portion of this, now A resolves to its value, which is 50. Is 50 less than 7? No, that's false. 50 is not less than 7. So this Boolean expression will boil to false. And for a conditional, for an if statement, we only execute the body of the if the Boolean expression was true. So this program would do nothing. It would display nothing to the screen. Okay, because 50 is not less than 7. But if I threw that else in there, now there's an otherwise statement, which is using game salad speak. We'll see it in rules here in a minute. But since A is not less than B, since this is false, it'll go ahead and execute whatever's in the else, which will print out A is greater than or equal to B in this case. Okay? So that's an example of a conditional in a high-level language like Java. Now, last time we talked a little bit about the various Boolean operators. We have our arithmetic ones that we're all familiar with. Less than or equal to, greater than or equal to, and not equal to. Then we have our logical Boolean operators, the ands and ors. So for an and to boil down to true, both sides of the and operator must be true. In order for the entire expression to be true. For an or, at least one side of the or operator must be true for the expression to be true. We gave some examples here. So 5 less than 7, that's a true statement. 5 less than or equal to 5, that's a true statement. 5 less than 3, that's false. 5 less than 3 or 7 greater than 50. Well, is 5 less than 3? It's not. So the left-hand side of this guy is false. 7 greater than 50? It's not. So the right-hand side of this is false. So this boils down to false or false, which is false. So that whole statement there is false. Okay? Similarly, if I took that same statement and I said 5 is greater than 3. Now the left-hand side is true. The right-hand side is still false. So we have a true or a false. And from this slide, or say that at least one of the sides has to be true in order for the whole thing to be true. So in this case, we do have a true on one side and we have a false on the other side. So since at least one side is true, this whole thing is true. Okay? Now, most of our modern programming languages, including in Game Salad works this way as well, when you're dealing with an or, as soon as it runs into a single true, it won't even look at the other side. Won't even check the second Boolean expression. This is a waste of time because it doesn't matter if this side boils down to true or false. Because since this first side was true, and this is an or, it's going to be true, regardless of whatever happens on the right side. Make sense? Okay, that can become important when you're solving some problems where let's say that you're working with just as an example, something called a string. So let's say that you have the string hello world, and the thing on the left-hand side asks if the length of that string is greater than 0, something like that, to make sure there's actually characters in the string. And let's say the right-hand side actually accesses one of those characters. Maybe the character at position 3 in the string, something like that. Well, if the string's length is not greater than 0, we don't want to start accessing individual characters in that string because they aren't there. Those are illegal positions. So only if the left-hand side is true, so let's just say we have a string named s, and the left-hand side says s dot length is greater than 0, we'll do it with an or first, and then we'll do it with an and, because the and actually makes more sense. Well, let's just do it with the and right off the bat, because they work the same way. And s.char at 0 is equal to the character A. Then go and do something. All right? So in Java, this is how we access an individual character in a string. Not important for us in here. Okay? But now we have a Boolean expression. That whole thing's a Boolean expression because it boils down to a single value of true or false. But on each side of the and, we also have a Boolean expression. The left side says s.length, whatever s is greater than 0. So the number of characters in s is greater than 0. So let's just use it as our example here. Let's say s is a variable that holds the string hello world. More than 0 characters in it, right? Hello world has several characters. So s.length, let's say it's 10, is greater than 0. That's true. So we'll go ahead and check the other side. And we'll access bucket 0 of that string. Now, let's say that s actually held the empty string. That is, if I say string s is equal to, that's a string containing nothing. That string's length is 0, meaning there's not even a single character in it. It's used for building other things. And we'll look at that later on in this class. So now we're asking, is s's length greater than 0? It's not. Its length is 0. Since this side boils down to false, and we're dealing with an and, the rules of the and say that both sides of the and must be true in order for the whole thing to be true. So since this left-hand side is already false, do we even need to ask about the right-hand side? Whole thing's false already, regardless of whether the right-hand side is true or false, because we failed over here. So not only would it be a waste of time, it's important for us to know in modern programming languages that this right-hand side will not get checked in the event that the left-hand side is false. If this string doesn't have any characters in it, we don't want to be trying to access one of the characters. That would give us an error. And we'd rather have our program not crash. Okay, so we're only going to ask this part of the question if this part of the question was true. Make sense? Okay, so that's kind of a rule of ands and ors, that if the first side of it fails, well, if the first side of it automatically makes the decision for the rest of it, really only plays into ands, I guess. So if this is a false and we're dealing with an and, it doesn't matter what the whole rest of the expression is. The whole thing is going to be false because it's an and. All right, so those are some examples of Boolean expressions. Now, I think I said back on this slide, asking questions. In Java, we do this through conditionals. That is if statements. And we've seen an if statement. In Game Salad, we're going to do this through something called rules. So let's go ahead and look at this in Game Salad. So we'll go ahead and open up the project we were already working on. So there's our Mario. And we're going to go ahead and go into our Mario actors blueprint, this guy right here. And over on this right-hand side is where we drag our behaviors. So for right now, what we're going to do, we can either go down and find the behavior called a rule, right here, or we also have a convenience up here called create rule, since we're going to be asking questions often. So we can go ahead and click create rule. Okay, and we have several, if we look at kind of how these rules are built, they're built in terms of this actor. So we can say, did this actor, in this case Mario, receive a specific event? That is, maybe the mouse position is over him. So if it's mouse position, it can be inside or outside of where he is. Maybe we've clicked on him. So think about this for like an iPhone. We've touched on Mario. Touched is pressed, touch is released. If we touch inside of where the Mario's hitbox is, so on and so forth. We can make it whether or not it overlaps or collides with another actor. So we'll look at that today. Auto rotation, that's a different event. We can do it based on mouse buttons as well. If the mouse button is down, mouse button is up, whatever. Okay, so let's go ahead and mess around with this rule a little bit. So by default, right now, if we go ahead and run, let me just get rid of this rule real quick. Okay, right now we have our pink box flying towards Mario. So let's go ahead and make this pink box stop moving. We'll still have it display its text, but what we did last time is we went into motion and we set the linear velocity on that guy. We hard-coded it at -100 to make it go to the left. So we'll set that back to 0. So now this dude is not going to be moving anymore. All right, so everything's static. Now what we're going to do is we're going to go back into the blueprint for Mario. We'll go ahead and create that rule. And let's do it based on a mouse click. So if we click down on the mouse, why don't we make Mario move? When we let go, let's make Mario stop moving. Make sense? Kind of an on-off type thing. So when the button is down, we are going to set an attribute. We'll change an attribute. What attribute are we going to change? Click on this. We want this actor's motion linear velocity on X to be equal to 100. Okay, so when we click down on the mouse button, anywhere on the screen, okay, this isn't related to Mario. Mario, he's looking for various events that can occur in the game. And when we click the mouse button down, Mario is going to start running. Okay, because it will become aware of this event that the mouse button is currently down. Therefore, we will set his attribute for linear velocity on X to 100. Otherwise, this is like our else. We'll just keep practicing with this. I'll change an attribute. What attribute? This actor's motion linear velocity on X to 0. When the mouse button's down, it'll be 100. When it's not down, meaning it's up, it'll be 0. That make sense? So when we first start the game, and we're not clicking the mouse button, it's up. So the linear velocity should be 0. As soon as I click, Mario starts moving. When I let go, Mario stops moving. Mouse down, set linear velocity to 100. Mouse up, set it back to 0. Make sense? Okay? And it's continually observing this. Okay, now this is something called the game loop. Okay. Now the game loop, we're going to say right now, is specific to Game Salad. Now, if you're writing video games in a more modern language like C# or C++ or Java or something like that, you would have to code your own game loop into it. Okay? Because games, when you start a game, things just don't start happening, and you can react to them. Things happen over and over and over and over again, right? If you're playing Mario, when you're running to the right on the scene, new guys are spawned, things are jumping up and down. When you kill a guy, he goes away. When you press the space bar, he jumps. Well, I guess not space bar, that's the emulators, right? So when you push the B button, for Mario, it's either button, right? You press A button and he jumps. But in any case, what's happening is that game has this thing called a game loop where it's running through all the things that are happening in the game, all the rules, all the attributes, all the stuff that each of the actors in the scene needs to be doing at all times. It's running through those over and over and over and over again so that the game is living. Okay? So if it didn't work that way, when this game first starts, I'll go ahead and hit refresh on it. If it didn't have a game loop and I haven't hit the mouse button, we've missed our opportunity for Mario to move. Make sense? We are reliant right now for it to constantly be checking, has the mouse button been pressed? 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 Over and over again. So that when we finally do click the mouse button, it catches that. Okay? So the question is how fast does that game loop have to go? Now, what we need to start thinking about is, in this little scene, there's very little going on, right? We have Mario, and we have a single box on the screen. And the single box only displays text, which is a constant action. And Mario listens for the mouse click event. But other than that, there's not things happening on the screen. We don't have, stuff, monsters coming back and forth and stuff flying through the air and all this stuff. So this would be, if you bought this video game, you would feel like you wasted your money, right? Not a whole lot going on. It's kind of like some of those 99-cent apps you get off the app stores. Like, what the heck is this? That's why the new strategy now is they make the app free, and then they put little tricks in there to try to get the kids to accidentally click on in-app purchase stuff. That's the way to make money now. I mean, because only about 50% of the parents complain. And I think you can set like parent features that are, my kid's not allowed to spend more than $2 in a day or in a month or something like that. So only if they exceed the $2 maximum does the parent ever find out. So, I don't know. Pretty crappy situation, I guess. All right, well, in any case, so there's very simple things happening on the screen here, but this game loop is constantly running in the background so that when I do, out of nowhere, press the mouse button, it detects it. Okay, so now the question is how much time does it take to go through all the rules associated with an actor? In this particular case, our actor is pretty simple, right? So here's Mario. He has one rule. We can rename the rule from generic rule to should I move? Because sometimes as our games start getting more complex, we might write a rule, put the details in here, and then we might compress it like that. So we don't see it. Kind of like that example of the telephone where we hide all the wires on the inside. If we need to get to the wires, we can come in here and make changes. But once it's working the way we want it, make sure you label it so you can find it again. Then you can just hit the arrow and close it. What you don't want to have is 30 of these that all say rule. Might be hard to figure out which one does what, right? So label them something that's meaningful to you. But in any case, in the big scheme of things, we would call this a fairly simple rule, right? It's listening for a single event, mouse click. When it's clicked, do one thing. When it's not clicked, do something else. All right? So while we were not clicking this, we were setting it to 0 over and over again. Okay, and we'll look at that as an example in a second. All right? Now, how long do you think it takes to ask this question? Short answer is not very long, but it still takes some amount of time, correct? Even if it's some fraction of a millisecond. Let's just say to ask this question takes 1 millisecond. Just using a simple example. Well, that's not very long from a human's perspective. Well, how responsive do we want our games to be? Let's say that when I pressed the mouse button, it took Mario 3 seconds for him to actually start moving. That wouldn't be acceptable, right? Okay, if you're playing Super Mario Brothers, which would be obviously a slightly more full-featured than what we have here, when you press the one of the buttons, you expect Mario to jump immediately. No delay whatsoever, right? Immediately. So the game loop needs to run often enough so that we are, as users, are at least convinced it's immediate, right? And more importantly, probably for a game player, is that it's consistent. Because as you start playing these games, you get used to the delay. There is a delay. When you first press that button, Mario doesn't instantaneously jump. There is some tiny, tiny, tiny millisecond delay. And then as you play the game, you start incorporating that into your strategy, right? You know you need to jump just slightly before you run into the flying turtle with the wings and the shooting the fireballs. Because it's bad if you run into him. You want to land on top of him. Okay, or jump over him, whatever. So you kind of learn that strategy. But those delays can't be random. That would make the game very difficult to play. If you hit the B button, and sometimes it happens instantly, and sometimes it happens in a second, and sometimes it happens in 5 seconds, the game would just be infuriating, right? Not going to work. Okay, so this game loop needs to do something often enough that it can keep up, but not so often that it's overburdened. Okay? Now, by keep up, we mean several different things. On one hand, we mean making the end user happy. I click the B button, Mario jumps. Well, there's more going on the screen than just the game engine sitting there waiting for you to hit the B button. There's all the other actors that are on the screen, right? So when a certain, like for instance, when you're playing Mario and you have the couple of different pipes, and a turtle bumps into a pipe, what does he do? Turns around and goes the other direction, right? So the whole time while the game's running, we have a second rule that we now know. We know it's waiting for the B button to be pressed, but now we also have the turtle actors constantly asking the question, have I hit a pipe? 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 And as soon as they hit a pipe, now what do they need to do? They need to flip their direction. So that's probably just an image transformation. And then change their linear velocity to be -1 times what it used to be, to go the other direction. Make sense? But it had to keep asking if I hit a pipe, if I hit a pipe, if I hit a pipe, over and over and over again before it finally made that decision. And we can start seeing as games get more and more complex. Think about our modern day, super realistic games. I use Battlefield pretty often just because there's a zillion things going on the screen at once. So imagine a game like that where there's so many things that are happening and each one has to do something, right? When something bad happens, something bad should happen. So if you're playing Battlefield and way out in the distance but still visible on your screen, a helicopter flies into a building, you don't expect the helicopter to just randomly just go through the building with no effect. You want to see explosions and the helicopter shrapnelizing and stuff flying all over the place, right? And then, you want the realism. You want to see people's limbs falling off there and all that stuff, right? Okay? So there's lots and lots of stuff going on in that. Relatively speaking, Mario is very simplistic, right? Okay? But part of this game loop is being able to keep up with all the things that are happening in your game, considering that the more complex the game, the more questions we're likely going to be asking every single time through the game loop. Kind of make sense? And that's why things start slowing down. So you get a more complex game on your PC, you got to start turning settings down on your PC because it doesn't have the horsepower to keep up. Okay? You can't turn settings down in your Xbox or your PlayStation. So the problem on those systems is on the developer side. They know the target hardware they're making their games for. So they need to make it work for those games. That's why typically when you are, when a game like Battlefield comes out for multiple systems, almost always the premium one is PC, right? Why? Because they didn't have to pay attention to fixed hardware. They could just say, we expected that you spent $6,000 in your gaming machine to make this look the best. Have at it. And so if you want to turn everything all the way up, full graphics, full, beheadings and stuff, you you can do that on the PC, but there's no selection on Xbox or PS4 because the people who wrote the game were writing it for fixed hardware. Now, we probably can assume that the game engines that they're using for, let's call it professional level, high-end gaming, are probably a little bit more robust than what we're dealing here with GameSalad. Okay? GameSalad is a small mini version of that made for games kind of like Angry Birds would be a good example of something you can make with Game Salad. Those types of games, that level of complexity. You're not making Battlefield with Game Salad. Well, you can try to make Battlefield with Game Salad, but it's going to start becoming very sluggish very quickly because of all the things that are happening on the screen at once. Okay, but there's an interesting problem that we have to consider that we don't really have control over. It's part of the decision-making process that they made when they built this game engine. And that is, what is the timing for the game loop? Okay? Each dude we have on our screen, so let's just give some definitions to game loop. So game loop specific to Game Salad and other game engines. Let's say it's the repeating asking of questions related to all of the actors in the current scene. Okay? And it could actually go into more than just asking questions, but since we're talking about asking questions right now, we'll leave it at that. All right? Now, each actor runs, well here, let's say each actor or actor type runs in its own, what's called thread. So a thread, well, let's talk about threads on another slide here. Thread is a lightweight construct in an operating system for your computer that mimics, well, let's say that tricks the user into thinking that more than one thing is happening at once. All right, so we need to talk about this through an example. If we go back to a much older operating system, now we're getting at possibly an age range issue. How many of you ever used Windows 3.1? How many of you were aware of the existence of Windows 3.1? Okay, so Windows 3.1, years and years and years ago. Last time it was really out was 1994, let's say. So that's really not that long ago, right? It's just 20 years. So when you were like 1, or if you're not 20 yet, before you were 1. Oh my gosh, I am old. Wow. So in any case, 94 doesn't seem like it was that long ago. I remember that. I remember 84. Oy. So anyways, Windows 3.1 did not support multitasking, something that we take for granted today. Most of us in here are probably Windows users. The couple of you that are Mac users, this translates right across. You can open 4 or 5 applications at once, right? No harm, no foul. Windows, when you don't want something bugging you, what do? You just minimize it to your taskbar, but you know it's still cooking, right? So if you open up your web browser, you start downloading a file, maybe let's say it's a 1 or 2 gigabyte file. I'm sure it's not an illegal movie, but you're going to put it in the background because on campus it's going to take anywhere between 5 minutes and 5 days to download that, right? So you minimize it so it's not bugging you. You know, you'll check on the download speed every now and then. Then you're off doing whatever. You're playing a game, or you're working on your term paper, or you're working on the homework assignment that was due 2 hours ago. Whatever it is, you have multiple things going on in your computer at once. You have your email running in the background, so it's checking every 2 minutes, whatever. That's something we take for granted today. But historically, that didn't exist. Your computer could do one thing at a time. Okay? And even in some of the early models of multitasking, Apple was a good example of this. Before Macintosh OS X, which is the current version of Mac, now they just keep coming out with updates to that same core operating system. But before that, we had Mac OS 9, OS 8, OS 7, OS 6, very inventive names. Now they started using cats, and they ran out of cats, and now they just start referencing things off the San Francisco coast. That was Mavericks. Now Yosemite's a park. But in any case, when you take an older Macintosh operating system like that, they had something called preemptive multitasking, which was like crappy multitasking for people who don't care. So what would happen is you open up a file, you open up a browser, you start downloading a file, and you minimize it, put it in the background. And then you open up Microsoft Word, you're working on your paper. 3 hours later, you go and check your download. What actually was happening is your download was given just enough CPU time for it to stay alive, but it wasn't actually cooking in the background. So you would look at it and, I guess back then, if you were lucky, it was downloading at like 1.2 kilobytes a second. That was considered lightning speed download back then. All of a sudden you look at it, it's downloading at like 200 bits per second. Like a lot slower because it wasn't given any CPU time. Well, it wasn't given very much CPU time. Better multitasking model is what we have in Windows and what we have in the Mac OS today. That is when you put stuff in the background, it's getting enough CPU time to kind of keep up its job, right? It maybe has a little bit less priority than what's in front of us, what we're actually working with, but we still expect it to be doing stuff in the background. Now, when we think about computers today, this is really the tool of the computer. Is when you buy a new computer, you're building a computer, you want there to be a fast processor, right? You want there to be lots of memory. Lots of memory means you can have more applications open at once. Fast processor means when you have more than one application open at once, it feels like they're all running at full speed all the time. Computers are really fast. So the whole job of the CPU in your computer is to fake the user out. Make you think that all the stuff you currently have open are all happening instantaneously. Now today we have even a little bit bigger advantage. Most of our computers today have at least a dual core processor. Some of them have 4 cores, some of them have even more than that. But historically, a processor could do exactly one thing at a time. A single core processor could do one thing at a time. So that means that if you had 5 applications open, I promise you, physically, only one of those applications was getting CPU time at any point in time. But now we have to talk about how human beings perceive time. We think about time in terms of, probably at the lowest level, seconds, right? Well, computers don't operate at seconds. They operate in milliseconds or fractions of a millisecond. Okay, so if Microsoft Word is getting 50 milliseconds, and then your download is getting 50 milliseconds, and then something else is getting 50 milliseconds, then it loops back around and Word gets 50 more. Download gets 50 more. This guy gets 50 more, 50 more, 50 more, 50 more, 50 more, 50 more, 50 more. And that's happening at lightning speed compared to how human beings perceive time. Now we're of the opinion that all this stuff is happening at the same time, right? Okay, so when you take the operating systems class, we talk about things like context switching and stuff like that. Like what's that balancing act, just like we're talking about here with our game loop. What's that balancing act between giving a program enough CPU time so it feels like it's accomplishing something, but not too much CPU time that the operating system now feels sluggish and the user gets pissed off. Does that make sense? So computers, it's all about balancing timings and stuff like that. And the ultimate goal is to trick the user to thinking that you are the most important thing in the world. Okay? So what a thread does is it allows more than one thing within an application to run at the same time. Before threads, we had processes. You can spawn off multiple processes, and the operating system itself would then schedule those processes to have this one run, then this one run, and this one run, then this one run, and this one run, then this one run over and over again. Have that happen fast enough that we're tricked out, like what we just talked about. But now a thread, this happens within an application. So, for instance, how many of you have ever been in a web browser and had multiple tabs open at once? All of us, right? We might have our Gmail open in one tab, and we might be doing some research on 2 or 3 other tabs. We might be bouncing back and forth between the 2 of them. We might be, searching for something else on another tab. So we might have several tabs open at once. Now, and you probably also have had a situation where you have a couple of different files downloading at once. That's something we take for granted today. If threads didn't exist, your web browser could do exactly one thing at once. Meaning, if you decided to download a 2 GB file, you were taking a break from using your web browser for right now. You couldn't do anything else within it because it was stuck downloading a file. Threads allow us to have multiple things within a single application act like they're all happening at once. So your web browser is getting scheduled on the CPU, like we just discussed, where it gets some CPU time, another program gets some CPU time, another program gets some CPU time. Well, threads are managed by an actual application so that within that application, when it's getting its CPU time, when Chrome is getting its time on the CPU, it decides I'm going to give some of my CPU time to this thread, some of my CPU time to this thread, some of my CPU time to this thread. Follow what's going on here? Okay, so these are all things we take for granted as computer users today, but they're happening all the time, and the whole goal is to trick us, to fake us out, to make us feel like our computer is fast enough. The reality is even with all this crap going on, our computers sit idle about 95% of the time. The CPU is literally doing nothing 95% of the time. Interesting backstory with this, when before dual-core CPUs, we had multi-CPU machines. So you wouldn't have a single CPU with multiple cores in it. You'd have a computer that had 2 CPUs in it. 2 separate CPUs, 2 separate fans, all that stuff. This is back when Apple used to make obvious mistakes. Now Apple pays somebody off and fakes their mistakes. But Apple came out with they called it the first supercomputer for consumers. And back when they still were using PowerPC processors before they switched to Intel. So this was during the time when it was the PowerPC G4 processor with AltiVec, which is like a multi-threading type model, kind of the predecessor to the Intel technology today called hyperthreading, which just sounds really cool, right? It's like hyperthreading must be good, okay, whatever that means. So in any case, they came out with the new G4s that had 2 processors in them. 2 heads is better than 1. This is during the time when OS 9 was still out. The one with crappy multitasking I talked about a little bit ago. Now, if you buy this new computer that has 2 processors in it, 2 processors, that must mean it's twice as fast, right? Okay, cool. Couple problems. First of all, not all problems benefit from having more than 1 processor. I don't know if we use the example on here or something like that, but how many people does it take to change a light bulb? It's not a 2-man job, right? So even if you bring an army of 30 people, changing a light bulb is not going to go any faster. Cleaning up a park might go a little faster with more people. That's a job that we can divide the labor up. So that's one problem. Not all tasks are divisible, okay? Bigger problem for that time period was OS 9 did not support multiple processors. So understand this. Apple is now selling this brand new product with 2 processors in it instead of 1, because 2 is better than 1. And that computer ships with an operating system that doesn't support the 2 processors that are inside of that computer. Okay, it's like a car coming with 4-wheel drive that doesn't have a button to turn on 4-wheel drive. Make sense? Okay, well, actually, it's probably worse than that. At least the car does have four-wheel drive. Well, whatever. Something similar to that at least. So what you were reliant on is specific applications could implement the ability to use multiple processors. So if you were running Photoshop back then, it could somewhat take advantage of your second processor. So it wasn't a total loss, but it was really not the advantage that they indicated you got when you saw the commercials and that kind of stuff. Okay, so it took some newer software that really started supporting multiprocessing correctly, and then we started getting into threading models where a single application could have multiple things happening at once. GameSalad is a single application. Okay, so here on this Mac, GameSalad is one of several programs that I have running right now. So I have all this stuff running on this Mac at one time. GameSalad is one of those programs. So it's already sharing CPU time with everything else. Now this guy has a quad-core CPU in it, and it has the hyper-threading awesomeness. So technically this computer can do 4 physical things at once. And through this technology called hyper-threading, which allows you to stage another instruction very quickly, you could sort of kind of do 8 things almost at once. Just say that's what hyper-threading is. Doesn't double your number of things at once, but it maybe makes it act like you could do 6 things at once if you're in a quad core, something like that. So let's say that GameSalad is getting one of the 4 cores at any point in time. Now, GameSalad internally is going to have several threads because I can be running this game. Let's go ahead and start it again. I could be running this game, and even when Mario is moving, well, right now he stops moving, but we know the game is running, I can still come up here and hit menus and stuff, right? Well, the ability for me to hit menus while at the same time my game is running down here requires at least 2 threads. Because I'm still interacting with the interface over here, while at the same time, Mario is down here. Notice when I am up here and I click, Mario doesn't move. It's only when I'm in the game scene does he move. So there's separate listeners going on here. Okay? So the idea there with that, I realize we're out of time, but the idea is that this multi-threading idea is very, very important for more than one thing to happen at a time in an application. The game loop has to take advantage of the fact that we have so many threads, one process, and we need to have all of our game elements all happening simultaneously-ish and still keep up with the user interacting with the screen. It's a hard problem to solve. All right, we'll come back on Monday. We'll talk more about the game loop.